I'm Chris Felton. I'm going to talk about myhdl and kind of this idea of mixing high-level synthesis at the same level of what I call event-oriented programming, but most people will just call it RTL. We had a conversation years ago about how there was this intermediate level of languages that came before Verilog and VHDL that were really RTL, and that Verilog and VHDL are, not RTL, but that was something else. So I call them event-oriented here. Some people call them simulation event-oriented, other things. This part of the high-level synthesis stuff I actually wrote a long time ago, but I never included it in the speech I was originally going to give. So this was a perfect opportunity to reuse that, recycle it. Also, I know this was right before lunch. Yesterday when I went through this, it took me 30+ minutes to go through my presentation, so I should be done in about 10 minutes so we can go to lunch. So kind of what I'm going to talk about, there's three parts of this, and this really is kind of the HDL developer stack. And so part of this is the myhdl. I'll give a quick overview of myhdl if no one's familiar with it. Then I'm going to give this kind of idea of the next level abstraction, which is kind of this interface-driven design. And then this last part, which is the high-level synthesis. What's interesting is a lot of what I'll be discussing really overlaps with what the current in Jack's presentation. It's a lot of the stuff, the kind of the specific properties of myhdl are similar to the chisel, but in a lot of ways very different as well. All right, so here we're kind of like what we're looking for in software. You're looking for a whole stack of tools and frameworks and stuff that you can use. So myhdl is one of the layers in that stack, and it's a fairly small, concise one. myhdl is Python. It's just a Python package. It uses the features in the Python language to implement this hardware description language in Python. So it uses the object-oriented features to define the signals and the bit vectors. It uses generators, which are kind of the micro-like threads. This is how we describe all the concurrency. And then it uses decorators to do some of the meta-programming to define your behavioral blocks. So that was the 30,000-foot overview of myhdl. Kind of a history. So it's actually, this project's been around for a long time. So the initial release was in 2003. It moved to GitHub, and 10 years later, the first ASIC was developed around 2010 with it. I started in the project around 2005-ish, 2006. First as kind of just a user, then started slowly getting more involved with it. Currently we have pretty infrequent release cycles, but our master on the GitHub is stable. We have a pretty large set of regression tests. But we do still maintain the project and add to it, but there isn't a whole lot of features that are necessarily being added to it. Everything else really focusing on developing up that stack. myhdl has actually a lot of VHDL influence from it. Jan, the original creator, if you look, he's written a bunch of stuff on the Sagasti website and some other places where he talks a lot about kind of his influence from VHDL, and some of that has worked its way into myhdl. Now I know a lot of times when people look at myhdl and they look at it, sometimes they feel like it has more of a Verilog. He did take kind of from both worlds to put this into Python. From the myhdl website, and the kind of the overview of myhdl we go through pretty quickly, but it's always good to know what it is and what it's not, and this was similar to kind of the chisel stuff as well. myhdl is not going to take a bunch of Python code and convert it into hardware and just have it work. Really, what it does, it gives you a package to describe hardware same way you do in Verilog and VHDL in Python. And then hopefully if you're familiar with Verilog or VHDL, when we look at an example, it will be relatively clear. Then there's a lot of stuff that it focuses on, just that really adopted from the Python language itself. And kind of mention this in some ways. I'll go through these bottom parts. It doesn't arbitrarily convert a lot of Python code. It's not radically a new approach. It's very similar to what you do with Verilog and VHDL. It's not a synthesis tool. It's a transpiler, like a lot of these other ones, so it actually will convert it to Verilog or VHDL. And that was mainly just a path of convenience, especially originally when these were generated. Of core project was created. That's not a core IP block library. That's something else that would be built on top of myhdl. And it's not just for implementation. I think this is one thing too, is that this is what I use it for a lot, is for system exploration, simulation, verification along those paths. So we have a website. You can go to the website. There's a bunch of information you can get there at myhdl.org. We have a set of documentation. I think the documentation is actually it's pretty good. We try our best to keep it maintained and up to date. This is kind of our set of core developers. So Jan did originally, majority of all the work early on. I think for the most part, he's kind of retired at this point. So there's a bunch of us that are carrying on. So we still, like I said, there's not a whole lot of new features that are being added, but we still fix bugs if we come across them. And for example, we have a new release that's coming up to remove the conflict of a new keyword in Python. So in one of our public APIs, we had async, and that is now a keyword in Python, so we'll have a release to resolve that. It's actually implemented in the master, so if you work off the master off of GitHub, it's already there and available. There's a forum, so there's a discourse forum where you can ask questions. And there's a few people that will answer questions on there. I think you pronounce it XS, maintains a list of a whole bunch of myhdl projects that are out there. So there's lots of different projects. A lot of them are relatively small ones, and there's some larger projects as well. This was a particular project I just wanted to point out. It's the filter design and analysis tool. So this is kind of a clone of the MATLAB tool. But this actually uses myhdl to generate Verilog or VHDL outputs of the filters that you may design in this. Now this is, like a lot of open source projects, it's kind of a fledgling project. Christian, who runs the project, does a really good job. But if anyone is looking for a project to contribute to, this is actually one that could be interesting. So here's a very simple example of myhdl. So in myhdl, in Verilog, you might call them modules. We call them blocks, and mainly because there was a overuse in Python. A file is called a module. So a lot of people that are familiar with Python would get confused when we call the hardware block a module. So we call them a block. And you have your combinatorial and your sequential logic that you can describe. And so this is kind of the generic block that you have in myhdl that looks, if you're familiar with Verilog or VHDL, this should look fairly familiar. One thing I point out here, so in each of these cases, so you can see that V is a signal, and it has an attribute that says next. And so closer to VHDL, you would set the next of the signal instead of having different operators for them. And so variables, if you use a variable, it would not have a next attribute, and you would just assign the variable directly. All right. The next part, so kind of moving up our software stack then, there's this idea of doing kind of interface-driven design. And I think in each language, the definition of interfaces is probably a little different, and so I'll try to explain how I use it here. And there's a couple packages that support this interface kind of framework. There's one that's called Ray, but I've been developing a package called Crux that I've been working on getting open sourced. So interface-driven design is fairly simple, right? So you take, instead of having all these ports into your block or module, we're just going to replace it with a couple simple interfaces. It's not a really new or complex idea, but surprisingly, especially in the Verilog or VHDL spaces, there is some limitations here. And in the myhdl and Python world, it's really simple. We all have an object, and if that object has signal attributes, it's your interface. And so the myhdl converter will take those and kind of just expand the names. And so you can use these interfaces and have as many embedded levels as you want and include the signals in there. Then kind of the powerful thing that I use quite a bit is that in these interfaces then, and it's just an object, you can define additional generators and functions to kind of implement transactors for your interface. But one of the things that I use quite a bit is that on a design, I'll have a set of inputs and I'll have a set of outputs and then something in the middle that does something with the data streams that might be coming in. And when I'm running top-level simulations and if I'm just trying to functionally work out what the middle part of my design is, I just replace those inputs and outputs with some transactor. I don't have to actually go through, if it's a serial interface, toggling all the signals just to get some data in and send it out. I can just replace it by a FIFO structure in software and just run the simulation. And then actually do the cycle accurate simulation on just the middle part of the design. One of the things that I found very useful is when you do kind of this interface-driven design is that, similar to a lot of the other stuff, but you can start scaling and managing the complexity of this a little bit more. So in this case, I have a whole bunch, I had multiple data streams that come in, and we'll go into a bunch of packet stuffers. And then those packet stuffers will be all coalesced into one output stream. And in this way, I don't have to ever define, I want 5. I have 5 input streams and I want 1 output stream. I have 3 input streams. I can just actually use a higher level set of kind of parameters to define my system. And that through the software, which is just Python, we can actually kind of manage that complexity. Now, this idea of managing complexity is very subjective and very, based on your opinion and experiences in a lot of ways. But here is just an example of creating those interfaces. There's a list of interfaces, and I create a bunch of instances of a packet stuffer in this case, and then I have one instance I coalesce all those. Here is just a very brief example that shows how you can use kind of the transactor generators in simulation if you wanted. And so you could actually, this would be kind of the reverse. If I had an interface and it actually represented a bus or something, I could say just write this, and the transactor could actually drive all the signals for that bus cycle. All right. I think I'm keeping true to racing through this a lot faster than I probably want to, but we're getting to the kind of the last part here now. So we kind of talked through 2 levels of this stack development, and then now here, there is an interest by some people and some groups to kind of mix in some of this high-level synthesis. And so here we're going to talk about some of the design patterns that we use in myhdl, which is kind of the decorators and the generators, and seeing if we can use that same design patterns and apply those to kind of describing some high-level synthesis. But before we get into that, I actually want to say, a lot of times you don't really even need the high-level synthesis. So similar to, again, Jack's talk had a lot of the same stuff. In myhdl is in Python, and since you have Python, you have what we call like a fully executable elaboration phase. So a lot of times you can just use this elaboration phase, just writing a bunch of Python code and taking all the different blocks or different pieces and combining those together to actually achieve the design or the description that you want to. So you don't really need a high-level synthesis. And a lot of times we're talking about here, and specifically in this talk, high-level synthesis will be taking a bunch of loops and extracting some hardware from those set of loops. So a couple years ago, I was looking at kind of a tutorial or a description of how to implement a median filter, and this was a median image filter, and it was an example used for a C-based high-level synthesis construct. And one of the things that caught me is in this description, when they were describing it, they said, well, one of the things you have to do first, before you ever even start doing this, you got to think about the problem differently. So what we have to do is we have to change the algorithm to kind of, so that you do this concurrent algorithm instead of just a simple procedural algorithm. And one of the things I thought that was interesting, because it seemed to be the opposite of what the high-level synthesis should do. Someone would go in and they'd write their procedural code and extract everything. And then in this tutorial, they're saying, no, do it the other way. And there's this tweet that kind of captures, I think it's kind of interesting in this way too, that in computer engineering and hardware engineering, we kind of think of C as a high-level language sometimes, then everyone else will think of it as a low-level language. So when they were talking about this median filter, what they wanted to do is they wanted to break out into this sorting network. And so what they wanted to do is not just describe the median algorithm, is that they wanted to describe this median sorting out this network. But once you break the problem down that way, you don't really need a high-level synthesis tool to do it. You can actually represent that fairly easy in a tool like myhdl or some of these other tools as well, that you can just construct the different parts, right? So you can describe, all your comparators. So each of those stages in the median network is just a bunch of comparators. So in here you'll have arrays as inputs, or we call them lists of signals in Python and myhdl. And you can generate a comparator that compares a bunch of those, a bunch of the inputs. So the for loop here is just walking through. It's taking the first two, creating a comparator, taking the next two, creating a comparator, and so on and so forth, so you can have as many inputs as you want. Now once you have your comparator, that first A stage of the comparator defined, you can string all the comparators together. Again, just saying, I have a whole instance of comparators, mapping the inputs, the outputs of one stage, the inputs of the next. So you don't really need once you've taken that jump of describing your algorithm in a more parallel fashion, you don't really need a high-level synthesis tool to grab it in that way. So I think in many of the cases, you don't really need a high-level synthesis tool. You need just this fully executable elaboration phase. And here's just a simulation run where over here you just have a model. I think I actually used like the NumPy median function or something, and run it with the actually converted Verilog. Run it and just make sure you get the same stuff. Included here just to show that the previous code was actually functional code that you could convert and actually create hardware out of. So, is there a case when we want to? So if we don't need high-level synthesis for a lot of these cases, is there a time when we want it? And the answer is there is times. There is times where we just have a somewhat complicated algorithm. We don't want to think about it differently. We just want to throw it to a tool and say, here, go with this. Especially if we just want to quickly prototype this algorithm and see if hardware, doing a hardware accelerator will be a good option for this particular algorithm. Doing floating point synthesis, a lot of times will be very useful as well. So we don't have to use floating point computational blocks. We can just kind of use our floating point variables and signals in our design. One of the big things that we want to do is, I think one of the current set of high-level synthesis tools don't give you is this ability to go back to your kind of behavioral description up to your high-level synthesis and back and forth and mix them together. So this was kind of the idea of mixing these together, is that in myhdl, if you use the same type of design patterns, that you can use a decorator to define your block, and in your block, which is just a Python function, but you've explicitly defined it as a myhdl block by using the decorator. Oh, this is a typo. This should actually just say like myhdl. Then you describe your behavioral blocks by using the myhdl decorators, and then you can describe the high-level synthesis blocks using a high-level synthesis decorator. So in this particular case, we're pulling out a couple interfaces that are defined in the high-level synthesis package as streams. And so this decorator will take this set of for loops, run it through its high-level synthesis compiler, and use the interfaces that are part of its package and identify those and actually extract hardware from those. Now note, this is exploration into how you would actually pull all these in together. These don't necessarily all exist. There's pieces of all these, but there isn't a package where you go pull all this and get this all to work at this point in time. Now the high-level synthesis part of it, where it actually takes all these loops and compile it, this is based on some work that was done by a group of researchers at Berkeley. So this was actually from a paper that was generated in the 2012 time frame. So what they did is they'll take all these Python loops, they'll extract the Python loops, do their transformations, and they'll generate the hardware from there. Now, to use this and pull this into the myhdl world, you wouldn't actually want to generate the Verilog in VHDL. You would want to generate almost, like the myhdl representation. The reason you'd want to do that is so that you could use the myhdl simulator and run it through the Python tools instead of having to also use the backend Verilog tools. So here's an example of the microarchitecture that is extracted from that high-level synthesis. So in that original example, we had 3 levels of for loops here, and so the compiler that was developed by the these folks would actually extract a hardware organization like this. Now some of the additions here would be is that using the interfaces would actually pull in, and you could, using the same interfaces, you could interact with your behavioral descriptions and with your high-level descriptions. So you could mix and match these code, and then the high-level synthesis compiler would extract this piece of hardware. So that was about all I had. So there was kind of those three parts of this kind of stack. We have the myhdl, which is kind of your behavioral descriptions, just like Verilog. The HDL, we have this interface-driven design that you use kind of the fully executable elaboration phase, and then the potential for including high-level synthesis in this design stack as well. And I think the high-level synthesis is useful because it will provide you with this kind of rapid prototyping of particular algorithms. All right, so that's all I had. Is there any questions?
Thank you for the great talk. My question is about pipelining. So most of HLS tools, after you synthesize a network, allow you to afterwards go and pipeline it certain way and change, number of pipeline stages you insert. How do you envision it in myhdl?
So in myhdl, or the high-level synthesis specifically? So back up here. So essentially how this would work is that in this decorator, you would have a whole set of parameters that you could add. So if you would say you wanted to automatically define the number of processing elements, if you wanted to define the number of pipelines, and et cetera. And so a lot of that, so some of that is part of the high-level synthesis tool that it will determine the number you want, but there also would be controls that you could give via the parameters. Then those parameters could percolate all the way up, and you can manage those in Python like you would with a whole bunch of different parameters.
So are interfaces recursive?
Recursive meaning that you can embed them inside each other?
I could take three interfaces, wrap a fourth one around, and run that fourth one up and down through the hierarchy, then to split out the original three.
If I'm following your example, yes. So because in each interface at each level is just an instance of that interface, and it just goes through those, and the converter just actually walks through each one and builds. And if you look at the actual output, it just has a really big name that pretty much represents the namespace of what you had. In those cases when you need them. In some cases, your signals actually simplify down to the original name. So at the top I'll have X, but then I put it into an interface and it gets embedded in some complicated thing, and at the end it just resolves back down to X. So in your converted output you'll just have X versus the hierarchical, the interface names all the way through. But yes, okay. They are recursive, you can embed them.
And second question, I take a parameter from my top level, I pass it down to an instance. I pass that through. Can I pass that parameter through an interface and pass that parameter to a second instance because they're plugged together?
Yeah, absolutely. Because that's actually one of the useful things you want to do is that you have an interface that you've configured some way, and now you want this block or module to deal with that interface and adapt to it as you need. Yes. Any other questions? All right, thank you.
I have a question in that case.
Yeah.
So as Jack said, I'm pretty interested in the IR part. Have you been looking anything at the back end, generating something other than Verilog and myhdl?
So we haven't done actually any work on it. There's been a lot of conversations. So within our group and our community, we've had a lot of conversations about it. There's been a lot of conversations external as well that we've kind of watched and taken part of. The issue is that so just using Verilog has just worked fine for us. It's been just a path of least resistance. And there doesn't seem to be a consensus on any other way. I think for our group and our community, I think we're really waiting for someone to pave that way. So for someone to take a stake, put a stake in the ground and say, this is the IR that we're going to use, make a bunch of progress, and then everyone else kind of, oh yeah, that was a good idea, and follow it. And I think we'll follow suit as well once that has. But yeah, we haven't really found one that fits all the needs for us at this time. All right. Well, thank you for having me. Thank you.